The story of a rebuilt supercar chasing its ultimate top speed is not just about speed, but about patience, engineering, and how modern machines behave when pushed to their limits. In this case, the focus is the legendary Bugatti Veyron, a car known for its extreme power and its famous 253 miles per hour capability in perfect factory conditions. The person at the center of this rebuild is content creator and builder Mat Armstrong, who is known for taking damaged supercars and bringing them back to life using a mix of skill, problem-solving, and bold decision-making. The goal of this project is simple on paper, but extremely difficult in reality. Take a heavily repaired Veyron, fix all its remaining issues, and attempt a full-speed run on a runway. The idea sounds exciting, but every step toward that goal reveals how complex and fragile such a machine can be when it is no longer in factory condition. Even before the speed test becomes possible, the car must be made fully functional again, which includes electrical fixes, mechanical repairs, and replacing parts that were either damaged or missing from its long and complicated history. What makes this story interesting is not just a final speed attempt, but the journey of getting there, where small problems repeatedly appear and force delays. Each issue, whether it is a fuse failure, a sensor fault, or mechanical misalignment, shows how sensitive high-performance engineering really is. A car like the Veyron is not just about horsepower. It is a system where every component must work together perfectly. If one small part fails, the entire performance chain can collapse. This introduction sets the stage for a story that is less about speed itself and more about control, persistence, and understanding how far a rebuilt machine can be trusted when it is finally pushed to its limit on an open runway. Before any serious speed testing can begin, the condition of the car must be brought to a level where it can safely operate under extreme stress. In this case, the Bugatti Veyron had already been through a long rebuild process under the hands of Mat Armstrong, but it still had hidden problems that needed attention. The early stages of preparation focus on restoring both appearance and function, because even cosmetic damage can hide deeper mechanical issues. The bodywork, for example, revealed inconsistent paint under previous wraps, which meant panels had to be resprayed properly to avoid long-term corrosion or mismatch in finish. At the same time, styling decisions were made to bring the car together visually, including a new wrap that changed its appearance significantly and made it feel more personal rather than factory standard. However, the more important work happened underneath the surface. The front splitter, which plays a role in high-speed aerodynamics, had been badly damaged in the past and required full reconstruction using carbon fiber techniques. This was not just about looks. At high speeds, even small aerodynamic flaws can affect stability. In addition, missing or damaged mounting hardware had to be recreated because original manufacturer parts were not easily available. This highlights one of the biggest challenges in rebuilding a hypercar outside official support: sourcing or recreating precision components that were originally designed for controlled factory environments. Every bolt, sensor, and fitting matters when a car is expected to reach extreme speeds. Even small oversights can turn into major failures later on the runway. During this stage, the car slowly transitions from being a broken project into something that feels whole again, but it is still not ready for real testing. It is in this phase that the tension begins to build, because everything looks finished on the outside, while the real uncertainty still lies in whether the internal systems will behave correctly under full load as the rebuild continues. Attention shifts from appearance and structure to the deeper mechanical and electronic systems that control the car's behavior. One of the most surprising discoveries during this stage is the simplicity of the so-called speed unlocking system in the Bugatti Veyron. This system is activated using a special key, often called the speed key, which is supposed to prepare the car for its highest performance mode by adjusting aerodynamics, ride height, and stability settings. However, during the investigation carried out by Mat Armstrong, it becomes clear that the key itself is not as complex as many believe. Instead of being a highly advanced electronic security device, it turns out to function mainly as a physical switch. This discovery challenges the idea that every part of a hypercar must be expensive or technologically advanced. In fact, even a basic mechanical copy of the key can trigger the same system, which raises questions about how much of the car's mystique comes from engineering and how much comes from branding. Alongside this discovery, several small but important mechanical issues begin to appear. Electrical faults such as blown fuses require careful testing of multiple circuits. since detailed diagrams are not easily available for such a specialized vehicle. This means each fuse must be checked individually until the problem is found. Another issue comes from ignition misfires caused by components not being properly seated during earlier repairs. Even a small misalignment in a coil pack can lead to engine instability, especially when the engine is under load. Once corrected, the engine returns to normal behavior, showing how sensitive modern performance engines are to small installation errors. These moments highlight a key theme of the story. Even when a car is rebuilt successfully, reliability is never guaranteed. Every system must be double-checked because high-performance machines do not forgive small mistakes, especially when they are expected to operate at extreme speeds as the preparation phase continues. More systems begin to show both progress and instability, revealing how interconnected the engineering of the Bugatti Veyron truly is. Under the supervision of Mat Armstrong, the team works through multiple technical problems, including tire pressure monitoring issues, hydraulic system behavior, and gearbox performance concerns. One of the more encouraging moments comes when aftermarket sensors are successfully recognized by the car system without official dealership programming. This suggests that some of the car systems are more flexible than expected, and that modern diagnostics can sometimes replace factory-level tools. However, this success is quickly balanced by more serious concerns. The gearbox, which relies on hydraulic pressure to change gears efficiently, begins to lose stability due to pressure accumulation problems. When the system cannot maintain consistent pressure, gear changes become unreliable and the risk of total failure increases. This is especially dangerous in a high-performance vehicle like the Bugatti Veyron, where transmission performance is critical for both acceleration and safety. A partial repair improves the situation, but does not fully solve the underlying weakness, meaning the car is still operating under uncertainty. Despite these challenges, the vehicle is eventually brought to a condition where it appears ready for testing. Warning lights are cleared, the engine runs smoothly, and most systems respond correctly. At this stage, the car looks complete from the outside, but internally it is still fragile. This contrast between appearance and reality creates tension, because it is difficult to predict how a machine will behave when it transitions from controlled testing to real high-speed conditions. The team must decide whether the car is stable enough to risk a runway attempt, knowing that even a small failure at high speed could stop the entire project instantly. As the final preparations begin, the focus shifts toward the runway test, where theory and repair work must face real-world conditions. The Bugatti Veyron is transported to a runway location where high-speed testing can safely take place, and all attention turns to whether the systems will hold under pressure. The weather conditions are not ideal, with a wet surface and uncertain traction, which adds another layer of risk to an already complex situation. Under the guidance of Mat Armstrong, the team carefully evaluates the car before any attempt is made, checking for fault codes, pressure stability, and overall responsiveness. For a brief moment, everything seems ready. The car enters its high-speed mode successfully, and the systems appear stable enough for a controlled test run. This moment is important because it represents the first time the rebuild feels fully alive again, as if all the previous work has finally paid off. During the initial run, the car performs well, accelerating smoothly and maintaining control on the runway. This creates optimism that the ultimate goal may actually be achievable. However, the situation changes quickly on the return phase when a critical electronic issue appears in the fuel system control module. Without warning, communication between systems is lost, and the car becomes unable to maintain normal operation. This failure is especially frustrating because it happens after all systems appear to be working correctly. The vehicle loses drivability, and the test run ends prematurely. This moment highlights a key reality of complex engineering. Even when most systems are functioning perfectly, a single electronic failure can stop everything instantly. The unpredictability of such failures is what makes high-performance automotive testing both exciting and difficult, especially when dealing with a rebuilt machine operating at the edge of its design limits. The final stage of the story leaves the outcome unresolved, emphasizing that high-performance engineering is often a process of continuous problem-solving rather than a single successful event. The Bugatti Veyron, even after extensive rebuilding by Mat Armstrong, proves that reliability at extreme speeds depends on perfect coordination between hundreds of systems working together at the same time. The failed runway attempt is not just a mechanical issue, but a reminder that age, previous damage, and small unnoticed faults can combine into major failures under stress. What makes this moment powerful is that the car had already shown it was capable of running, accelerating, and entering high-speed mode successfully, yet it still failed at the final critical stage. This creates a sense of unfinished progress, where success feels close but not fully achieved. It also reflects a broader truth about complex machines. They can behave perfectly for long periods and still fail suddenly when pushed beyond normal conditions. The story does not end with a successful top speed run, but with a breakdown that forces further investigation and repair. This unresolved ending keeps the focus on continuation rather than closure, suggesting that the journey is still ongoing. In many ways, this is what makes the story compelling. It is not just about reaching 253 miles per hour, but about understanding what it takes to even attempt it with a rebuilt hypercar. The final moment reinforces the idea that engineering success is not a single achievement, but a series of attempts, failures, and improvements that slowly move closer to the goal. After the runway failure, the focus quickly shifts from excitement to deep problem solving, because a breakdown at high-speed testing is never just a small issue. In the Bugatti Veyron, the fuel system is one of the most important parts of the entire car, and when the fuel pump control module stops communicating, it effectively shuts down the heart of the machine. This is not a simple part that can be ignored or reset easily. It controls how fuel is delivered to the massive engine, and without it, the car cannot maintain power, even if everything else is working perfectly. Under the work of Mat Armstrong and the team, the situation highlights how modern hypercars depend heavily on electronic systems working in perfect harmony. Unlike older cars that rely mostly on mechanical systems, the Veyron uses layers of electronics, sensors, and control units that constantly talk to each other. If one unit stops responding, the whole chain can break. What makes this failure even more frustrating is that there were no warning signs before it happened. Everything looked normal during the run, and the car even completed a successful high-speed pass earlier. This randomness is what makes diagnosing such problems very difficult. The issue could be caused by heat, vibration, electrical fatigue, or even a loose connection that only fails under stress. Another challenge is the age of the car itself. The Veyron is no longer a new machine, and over time, wiring, connectors, and control modules naturally weaken. Even if the engine and major parts are strong, small electronic components can become unreliable. This is especially true when a car has been repaired and modified multiple times in its life. Each repair adds a small risk of imperfect reconnection or stress on wiring systems. So what looks like a sudden failure on a runway is actually the result of many small weaknesses building up over time. This moment shows that in a hypercar, performance is not just about power or speed, but about perfect reliability of thousands of tiny parts working together under extreme conditions. This situation also reveals a deeper truth about rebuilding complex machines like the Bugatti Veyron. When someone like Mat Armstrong takes on a project like this, it is not just about fixing damage or making car run again. It becomes a test of understanding how far a highly engineered machine can be restored outside its original environment. Manufacturers like Bugatti design their cars to be maintained using special tools, factory procedures, and control systems. When those systems are removed or replaced with independent solutions, unexpected problems can appear. Some people believe that modern hypercars are impossible to maintain without official support, while others believe that with enough skill and patience, almost anything can be repaired. This project sits right in the middle of that debate. On one hand, many parts of the car have been successfully repaired using independent workshops, custom solutions, and careful diagnostics. On the other hand, the sudden electronic failures show that some systems are deeply sensitive to factory-level integration. Another important lesson is that cost does not always match complexity. A small and cheap component, like a fuse or connector, can stop a multi-million-pound machine from working. This creates a strange contrast where extreme engineering depends on very simple parts functioning correctly. It also highlights how important patience is in automotive repair at this level. Every issue must be traced carefully, because guessing or rushing can lead to more damage. In many ways, the rebuild becomes less about money and more about understanding. It shows that even the most advanced cars in the world still depend on basic principles: clean power, stable connections, and precise communication between systems. When any of these are broken, even the most powerful machine becomes useless until it's fixed again. The project continues beyond the failed runway attempt. The next steps become focused on rebuilding confidence in the system before another speed run can even be considered. The Bugatti Veyron is not simply repaired once and finished. Instead, it enters a cycle of testing, failure, and correction under the hands of Mat Armstrong. The team begins to break down the failure logically, trying to understand whether the fuel pump control module was the root cause or just one symptom of a larger issue. This kind of investigation is slow and detailed, because replacing parts without understanding the cause can lead to repeated failures. Wiring checks, connector inspections, and system resets all become part of the process. At the same time, there is a strong emotional pressure building, because the car has already shown that it can reach high-speed conditions, but it still cannot complete a full successful run. This creates a feeling of being very close, but not finished. The team must also consider whether the runway conditions, weather, or vibration played a role in triggering the failure. Sometimes problems only appear under very specific situations, which makes them difficult to reproduce in a workshop environment. This is one of the hardest parts of working with advanced machines. A fault that appears once at full speed may not appear again.